Hello, my name is Chase. This is Headframe Energy Services, and we are from the Petroleum Department, one of two different presentations today. Developing our reservoir was pretty key to this project, and so to do so, it was necessary to understand the lithology, the reservoir properties, and lithologically speaking, the reservoir was very homogeneous dolomitic sandstone. And so the reservoir itself is bounded by a shale on top and bottom, which created a sealing lithology. And on average, the reservoir was approximately 9,700 feet deep. And so it was possible to create a unique gamma signature due to the shale layers. From the log and core data, it was possible to determine the necessary properties to model the reservoir, such as water saturation, porosity, and permeability. And these properties were all obtained through log correlations and volumetrics. The reservoir is designed using a 4-layer model consisting of upper, lower, and middle Bakken, as well as the Three Forks, with Eclipse 100 black oil used for a 10-sectional area. The reservoir was designed with homogeneous layers that were modeled horizontally with an effective permeability that was locked. It was used to conduct spacing and production analysis by simulation. And so as a result, 1.7 million stock tank barrels were recovered from the two-sectional area, and if applied to the entire field, it may yield up to 8.5 million stock tank barrels. This is the drilling rig that was used to drill the wells. The rig featured three 1,600 horsepower motors and has the ability to rack 800,000 pounds of drill pipe. The rig also can walk 2 feet per minute with 800,000 pounds of pipe racked. All of these wells will be drilled horizontally and have an average depth of 20,000 feet measured depth, 10,000 feet true vertical depth. The average kickoff point is around 9,200 feet true vertical depth, and that is where we will start to build the curve. The curve is built very quickly at 11 to 12 degrees per 100 feet, reaching 90 degrees in less than 2,000 feet. From our design, artificial is used as a mechanism to increase the flow rate of oil and gas to the surface from the producing wells using assisted lift technology. We decided to use the electronic submersible pumps for the early stages of production due to high volatility of the oil alongside the high volume produced during the 15 months of production. The D-series pumps were chosen due to their capacity measurements in handling the broad ranges of production that encompasses the first two stages of volatility. And with the beam lift being introduced in the 16th month as a long-term solution for under 200 barrels per day for each well once the capacity has reached that margin. The beam lift shown above depicts a horse head device to pump gas into the well in order to artificially increase the ability of the oil to rise to the surface. The electronic submersible pump shown on the right is there to visualize the motor, pump, lift system as a 2D model. As the oil and gas travels from the artificial lift system, it reaches first the separator, which is a pressure vessel used for separating the fluid components of an oil and gas stream into both gaseous and liquid constituents. The first stage of the gas from the separator is then transferred to the glycol dehydrator, which is a liquid desiccant system for the removal of water from natural gas and natural gas liquids using different forms of glycol. After the gas travels through the dehydrator, the natural gas is sent to the compressor to further translate the gases temperature and pressure to pipeline restraints where the gas will be sent to the treatment facilities less than 100 miles away. The oil from the separators will be transferred into heater treaters where heat and mechanical separation devices are used to facilitate the separation of oil and gas emulsions before transporting the dry oil through pipelines. The dry oil is then collected from the heater treater and then processed through the stock tanks until the oil is sold and sent through the pipeline to midstream operations. Both the water from the separator and the water from the heater treater are put into the water stock tanks, which are then sent to water treatment facilities less than 100 miles away. Hydraulic fracturing is a very necessary part of the butte formation because of the permeability being so low and the oil will not reach the wellbore at economic quantities unless we fracture the formation. And with hydraulic fracturing, we inject a fluid called fracture fluid at a pressure greater than the formation can handle to initiate the fractures that we actually need. The proppant that are used is sand to hold the fractures open when the fractures process has actually stopped and the formations start to close. Water-based fracturing fluid is the most common for our project, using slick water, which is water used with some additives created for the necessary fracture. The proppant used is Ottawa sand, and it's typically found in western USA, with a total of 120,000 barrels of fracturing fluid and 8.4 million pounds of proppant will be used during this fracturing process. The field we were working on has 14 wells that were previously developed. As you can see from the costs here, we have the cost per well and the cost of the 13 wells. And since we are developing the 13 new wells, each of the costs were multiplied to 13 to account for the entire field. With revenue being a very important part of this project, we calculated the development of the field to ensure a profit. Using the production data from a simulator, 3 oil price scenarios were considered to account for possible oil price fluctuations at 25, 50, and 75 barrels respectively, 25, 50, and $75 per barrel respectively. As we can see from the tables, our profit for each scenario increased almost $100 million, which guarantees the development of our land to be successful. Thank you for coming to our presentation, and this is Headframe Energy Services.